Bayes Theorem in action. An example.
Imagine the following scenario. You are generally a healthy individual. While at work, you start feeling slightly unwell, not experiencing any specific symptoms, but generally not at 100%. Concerned, you go see a doctor. After an examination, the doctor cannot determine the cause of your discomfort and recommends a comprehensive series of tests. A week later, the results come in. They reveal that you have tested positive for a rare and severe disease. This disease affects only 1 out of 1,000 in the population. Alarmed, you ask your doctor, "How confident can we be that I actually have this disease?" He explains that the diagnostic test correctly identifies 99% of individuals with the disease and incorrectly identifies only 1% of healthy individuals as having the disease. At first glance, it might seem logical to conclude that the probability of having the disease is approximately 99%, given the accuracy of the test. However, this is not the correct interpretation of the results. To determine the true probability of having the disease, given a positive test result, we must consider not only the test sensitivity and specificity, but also the prevalence of the disease in the population. This is where Bayes' theorem provides critical insight. Using Bayes' theorem, we calculate the probability of actually having the disease given a positive test result. In other words, the true probability of having the disease given a positive test is equal to the probability of a positive test given the disease times the prevalence of it in the population divided by the total probability of testing positive. The total probability of testing positive accounts for both true positives and false positives. So, the probability of having the disease given a positive test result can be calculated to be approximately 0.0902. That is only about 9%. Despite the test's high accuracy, the rarity of the disease leads to a much lower probability than one might intuitively expect. Let's try to see if this makes any sense. Here we have a grid with 1,000 cells. Each cell represents an individual. Since the prevalence is 1 in 1,000, on average, we expect one individual in this population to have the disease. If we tested the entire population with a test that gives a false positive 1 out of 100 times, we would expect to get a result that looks like this, where the yellow circles are those whose test results were positive. As we see, there are 10 false positives and 1 correct positive. So, if we group all those that tested positive, we have something like this. We can clearly see here that out of the 11 people who tested positive, it is likely that only 1 actually has the disease. So Bayes' theorem tells us that after a positive test that is 99% accurate, the real likelihood of having the disease is about 1 out of 11, or only 9% due to its low prevalence.